Alright, so now let's go through a few general strategies for how we can solve problems in caches. The first thing to remember, and this is a common source of confusion or question that we get, is who defines the address size. So the address size is defined by the ISA. So that's why we talk about 32-bit ISA or a 64-bit ISA, etc. So what that means is the address size is 32 bits or 64 bits, depending on which ISA you're talking about. And that information is visible to the programmers and the compiler. Now, the cache design, on the other hand, the details of that is hidden from the programmer and the compiler. As a result, the cache design details are not specified as part of the ISA. So when you are given an address, and for a given cache design, you have to interpret that address into these three different fields: tag, line index, and block offset. That interpretation is specific to a cache design. And so it's a cache that takes the address and partitions them into those three fields. The details of how to do that is invisible to the programmer and the compiler, and they're not really part of the ISA. And that's why a cache design can vary from one processor implementation to another, even though they both may support the same ISA. Another common source of confusion is in understanding the difference between the byte addressable versus word addressable ISA and its impact on how to compute some of the details for cache configuration, in particular block offset. So let me briefly recap what byte addressable ISA versus word addressable ISA is. So if an ISA is byte addressable, what it means is any given address refers to a memory location that stores exactly 1 byte of data. Okay, so if I have a memory and if I address it sequentially through addresses ranging from 0 to n, each address refers to a memory location that stores exactly 1 byte worth of data. In the case of a word addressable ISA, each address refers to a larger data item, and that size is the size of the word. So instead of a byte, it would be a word. Now you may question, okay, what is going to be the size of the word? Now, in common practice, a word is usually the same size as the number of bits that you're used to describe the ISA. So it changes from one ISA to another, unfortunately. So byte is just 8 bits no matter what ISA you're talking about. But a word, the size changes from one ISA to another. So if I'm talking about a 64-bit ISA, a word is going to be of 64 bits in size. If I'm talking about a 32-bit ISA, a word is going to be 32 bits in size, right? And so you need to factor that into the size computation. Now, why are we talking about these differences? Because you'll see that in some of the problems posted online from previous exams, they may tell you whether the ISA is byte addressable or word addressable, and that has a significant impact on how we compute the size of the block offsets. Let me explain. So block size is usually defined in terms of bytes. So I may say my cache block size is 256 bytes. Fine. Now to figure out what should be your block offset size, so far what we've been saying is just do a log to the base 2 of the block size that is given to you. So if it is 256 byte block, say it's 256, and then you will figure out that, oh, it's 8 bits. Now that's a reasonable assumption to make, provided that each individual byte within your block is addressable. Meaning, if it is a byte addressable ISA, that assumption is a valid assumption. However, if your ISA is word addressable, then you have to remember that I can only address memory locations in chunks of word. I cannot address individual bytes within a word. So therefore each address refers to one word in a cache block. So therefore my granularity is now much larger, which is a word. And now I have to think about the block offset as how many bits do I need to distinguish the different words in that block, right? And so one has to then figure out how many words do I have in a 256 byte block, right? So all that matters is how many addressable data items do I have in a cache block. That's what matters when you're trying to compute your block offset. So if it is a byte addressable ISA, the number of addressable data items is exactly the same as the number of bytes, and that's why this computation was correct. But now if it is a word addressable ISA, you need to compute the number of words in a block. Now for this example, it would be 256 bytes divided by the size of a word. The size of a 64-bit word is going to be 8 bytes. So I would have a total of 32 words in this block. So if I have only 32 addressable data items, then my block offset has to be only of size log to the base 2 of 32. So it's going to be 5 bits. So for the same block size and for the same address size, right? So same cache block size and same address size, 64 bits, I can end up with two different block offset sizes depending on whether it is word addressable or byte addressable. So that's something to keep in mind when you are parsing through the cache problems. So I talked about a few equations in the last lecture. I would like to go through them again because it's quite important and useful when you're looking at cache problems. So the first thing is the number of cache lines is same as the number of cache blocks. So these two terms are often used interchangeably, but to me, a cache block refers to the cache block of data. Cache line refers to the hardware structure that stores the cache block along with the metadata such as the tag, LRU bits, and the valid bit. But in terms of the numbers is exactly the same, and that's one of the reasons why they seem to get used interchangeably. The way to compute the number of blocks, or the number of cache lines, is by dividing the cache size divided by the block size. That's pretty straightforward. And the number of block offset size would depend upon the block size. So log to the base 2 of the block size is going to be a block offset size. Alright, so now we need to compute the number of sets. The easiest one is a fully associative cache because the number of sets is always 1. Doesn't matter what your cache size is, doesn't matter what your block size is. Number of sets in fully associative cache is always 1. Why is that? Well, the way to think about it is in a fully associative cache, all the cache lines are part of one single set. And a cache block therefore can be stored anywhere within that set, which consists of all the cache lines in the given cache. So the other extreme, we have the direct mapped cache. Again, it's fairly easy to compute because all you need to do is to take the number of blocks and then you know the number of sets because they both are exactly the same because the number of cache blocks per set is 1. Now let's talk about two-way set associative caches. In this case, the number of cache lines per set is 2. So I have to take all the lines I have, divide them by 2, and then I will be able to compute the number of sets. So every set will have the number of sets will be half as many as the number of lines. I can generalize this and say, well, if I have an n-way associative cache, then I would divide the given lines by the number of ways to compute how many sets I get, right? So once you have figured out the set number of sets, computing the set index size is trivial. Just take a log to the base 2 of the number of sets. And once you have your block offset size and the set index size, you subtract those from the given address size. Again, that's defined by your ISA. Then you get your tag size. Let me talk about the 3C problem first before I talk about the cache performance. So in the case of a 3C problem, it's common to think about to recap what we talked about, 3 types of cache misses. We want to understand the type of cache misses that we experience for a given cache. So I take the cache, I take a look at its geometry, and you look at the address sequence X, Y, Z, right? And then you ask yourself, oh, I see some hits and some misses. And you want to understand why you are experiencing some misses. What is the reason for those misses? And to understand what type of misses you are incurring, you need to simulate not only the given cache to figure out what these hits and misses are, but you also need to simulate 2 more caches, an infinite cache and a fully associative cache. Let's see how to use those 2 caches to classify the misses that you observe in the given cache. Okay, so the question we are asking is, you're given a cache, let's say 2-way set associative cache with some sort of block size and some number of cache lines. So you know what your cache looks like, and you went and simulated it. And after simulating it for an address sequence, you were able to figure out which addresses were hits and which addresses were misses, and you're asking yourself what type of a miss is each one. And to answer that question, the first thing you need to find out is this miss for a given address also a miss in the infinite cache? And if the answer is yes, then you would say it's a compulsory miss. And the way to think about it is, if a miss in the given cache is also a miss in the infinite cache, then no amount of capacity or no amount of associativity is going to turn this miss into a hit, and therefore the miss is compulsory. And the only way in which you could reduce compulsory miss is by increasing the cache block size to exploit more spatial locality. Okay. Now let's say the miss turns out to be a hit in the case of infinite cache. So then what do? Well, you ask the second question. Is that miss that I saw in the given cache, is that still a miss in the fully associative cache? And if the answer is yes to that second question, then you will say, well, then the miss that I saw in the given cache is actually a capacity miss. Why is that? Well, even with the best possible associativity, which is a fully associative cache, I still incurred a miss. So the only way in which I could solve this problem is perhaps by increasing the size of my cache. Now this is a little bit of imprecise statement to make, because in the case of a fully associative cache, I need to assume a replacement policy, typically an LRU policy. So the miss that you may be encountering could be because of the replacement policy, but we're going to make approximate assumption, if you will, to sidestep that issue and say, well, if I see a miss in the fully associative cache, then I'm going to assume it's a capacity miss. And that's a fair assumption for the common case, because you're assuming an idealistic situation with respect to the associativity. And so so you can say that, well, the reason why I got a miss is really because of lack of space, right? Not necessarily because I had a poor replacement policy. All right, so now let's say you found out that the miss in the given cache is not a miss in the infinite cache, not a miss in the fully associative cache. Then you're left with only one choice, which is the conflict miss. right? Because it tells you that it's not a capacity miss, because it was actually a hit in the fully associative cache. And so the reason why you ended up with a miss is because you reduced the associativity to something smaller, maybe 2-way or a 4-way set associative cache or an 8-way set associative cache. And so if you were to increase the set associativity, then maybe you may be able to get rid of this miss. Okay. So to summarize, you take the given cache, simulate it for the given address sequence, and figure out which one is hit and which one is miss, which addresses are hits and which addresses are misses. And to figure out whether those misses are, to figure out the type of those misses that you just discovered, you need to simulate 2 more caches. The first cache is the infinite cache, but you need to assume the same block size as the given cache. And the second one is a fully associative cache. Also assume the same block size, but now you're going to have a limit on the size as well. And so you go and simulate those 2 caches, figure out what the hit and misses are. You take all that information and then go through this algorithm that we just went through, and then you'll be able to classify the sequence of misses that you observed for the given cache into one of these 3 types. Now, I talked a lot about simulating caches, and you may be asking yourself, what do I mean by simulating a cache? So a cache simulator, essentially what it does is, for a given cache configuration, right, for a given cache size, associativity, block size, etc., it abstractly models that cache. I'm representing that abstract model here. And then for a given address pattern, the given address pattern, the cache simulator tells me which one is a hit, which one is a miss, and so on. So cache simulator basically says some of them are hits, some of them are misses, and so on. I'm just randomly assigning these roles. They don't have any meaning, right? But basically a cache simulator for a given address pattern will be able to say which one of these addresses. So this is the address pattern. So this is the address pattern, and the cache simulator computes whether each address in that sequence is a hit or a miss. So that's what a cache simulator does for a given cache configuration. So in order to do that simulation, what the cache simulator has to do is it take each address and split that into these 3 fields. And we talked about how to split a given address into these 3 fields before. And then model the cache. Now, one of the tricks that you want to use is when you're modeling a cache after this point, once you have computed what your tag and set index is, then that information alone is sufficient to then go and simulate the cache. I don't really need the block offset. In fact, I don't need the data, nor do I need the block offset after that point, because the state of the cache only depends on the tag and the set index. The block offset is only going to be used to access a byte in a given data, which is very important in the processor to grab the data, but to simulate a cache and figure out hits and misses, you don't really need that. The final thing to implement while you're doing a cache simulation is to keep track of the LRU rank for the cache lines. And the algorithm that we talked about for that is for the cache lines within a set. Let's say you have 4 of those. I need to keep track of a counter. I'm going to call that as a LRU counter. And that counter is going to keep track of the LRU rank. Higher the rank means it's least recently used. Higher the rank is bad. Now when I access a cache block within the set, I'm going to set its rank to 0, meaning it's the most recently used block. And then I have to increment the counter for all the other cache lines. And when I have to pick a victim, I'll pick the cache line with the highest LRU counter. So that's one way to implement the LRU rank and replacement policy. And keep in mind that other replacement policies do exist. Another one would be most frequently used policy, in which case you would say if a cache block is most frequently used, then I don't want to evict it, etc. So I don't want to go into the different replacement policies, but the point here is that when you're simulating a cache, you need to simulate the LRU rank for the cache lines within a set. So one thing I need to clarify here is that in the fully associative cache, you will be maintaining the LRU rank across all the cache lines because all the cache lines are part of one single set. But in the case of a set associative cache, that is not true. So let me say that I have a four-way set associative cache, let's say. So these little boxes that I'm drawing each represent a cache block within a set. So I have two sets here, and I have four ways. And the point I was trying to make is that the replacement policy need to bother about only the blocks within a set. So the LRU rank will be maintained across the blocks within each set. So let's say that I have accessed all these cache blocks, and it turns out that the least recently used cache block across these four happens to be this one, so then I will choose that to be evicted. Now it may be the case that set 1 contains really old cache blocks that the program has rarely ever accessed, right? And so in that case, you would say, well, that's not a good idea. Why not replace one of these really old cache blocks in set 1? Well, you can't do that because in the case of a set associative cache, for any cache block, you only have the option to store that cache block within one of the four cache lines within the set where you can store that cache block in, right? So LRU across the sets doesn't make sense. You need to implement the LRU policy within a cache set. All right, so in addition to being able to simulate a cache, it is important to understand how to reason about a cache's performance. And we talked about this metric called average memory access time in the first lecture on caches. And I would like to clarify one common source of confusion that you may have when you look at the problems from the previous semesters. And that is due to the the difference in assumption we make about the memory latency. Now let me talk about the most intuitive way to calculate AMAT, and then I will clarify this variance. Now, one important thing to understand is every memory access first accesses the cache, and if it's a hit, you're done. But if it is a miss, then you go and access main memory. So when you're thinking about average memory access time, you're trying to ask yourself, on an average, how long does a memory access take? Well, if all of them are cache hits, then the average memory access time would be just the cache latency. But that's of course not true, because for some fraction, which is defined by the cache miss rate, for some fraction of memory accesses, I would have to additionally incur the latency of accessing the main memory. So therefore, the way to calculate the average memory access time is by adding cache latency with memory access latency and multiplying that with the miss rate. That seems fairly intuitive, right? Now, this is true, this way of calculating AMAT is correct only if we assume that the memory latency does not include the cache access latency. Now that's a reasonable way to think about it, right? So I would specify, okay, what's the time it takes to access main memory, what's the time to access the cache, so you can plug those numbers in and compute AMAT. That's correct. But sometimes in a few problems, they may state that, assume the memory latency includes the time to access the cache. So now what that means is, when I say some fraction of cache misses, I incur the latency of memory, that latency includes the cache access latency and the main memory latency, right? So it already includes the cache access latency, and therefore you don't need to double count it. And that's why it's important to attribute the cache only latency to the fraction of accesses that are cache hits. So the fraction of accesses that are cache hits would endure cache latency. The fraction of accesses that are misses would endure the memory latency, which includes the cache latency, and that is consistent with our view that every memory access first checks the cache and then goes to the main memory. Okay, so look out for this assumption when you are looking at the cache problems. Does the main memory latency include the cache access latency or not? If it doesn't include, use this equation. If it does include, use this equation. And we'll always try to make it clear which one of these assumptions we are making in our problems.